Hi, welcome to the seventh session on group theory. We are continuing with the symmetric groups. In the last session, I ended the session with the following statement that any permutation can be written as a product of transpositions, and while this way of writing is not unique, the number of transpositions involved in that expression will have the same parity. That is, if sigma equal to sigma 1 to sigma k and is also equal to tau 1 to tau L, where sigmas and taus are transpositions, k and L may be distinct, but k is even if only if L is even. That is, k and L are both even or k and L are both odd. This is what we wanted to prove. Okay, and I will explain the basic idea what it is, and then we will use a modern algebraic tool to prove that. Okay, it depends upon the notion of number of inversions. Okay, what does it mean? Suppose I take, okay, let us n equals as usual greater than or equal to 2. Let us assume the ordered pair I, j, where I is less than j. Like for example 2, 5. Right? Now if sigma is a permutation, I apply to that. What do I get? I get ordered pair sigma 2, sigma 5. But sigma 2 may not be less than sigma 5. Right? It may be sigma 2 greater than sigma 5. That means that sigma, I say, you introduces an inversion for the ordered pair. Okay. Oh, it may, some of you may find it easier if I write these things. Let us look at it. Okay. So, what you want to do, the thing. So, as usual, n greater than or equal to 2 and sigma is Sn. Now, let us look at ordered pair ij with I less than g. Okay, of course, 1 less than or equal to I, less than or equal to n. Then I look at the corresponding ordered pair sigma I, sigma j. Right? It may happen sigma I is less than sigma j, then it's okay. But if sigma I is greater than sigma j, notice that they cannot be equal because I and j are distinct. Sigma is a permutation, particular is a bijection, and 1 1. Therefore, sigma I and sigma j are distinct. By law of trichotomy, either sigma is strictly less than sigma j or sigma is strictly greater than j. If this happens, okay, okay, we say that sigma introduces an inversion. Okay, right? Now, let us think carefully. I have the set 1 to n, right? And how many ordered pairs ij I can find such that I is less than j? How many such pairs exist? Notice that if I look at this set, okay, the number of two element sets is n choose 2, right? Number of two element sets is n choose 2. That is nnt n minus 1 by 2, right? Therefore, given any I and j, two elements at I not equal to j, by order relation I can as well assume I is less than j. Okay. And conversely, you give me any ordered per I j, I less than j, I get a two element set. Therefore, there is a bijection, right? So, make sure you understand this. Okay, right. So, let us look at all two element sets. Let me call it, okay, T for two element sets. That is R, two element subsets of 1 to n, which is same as saying, let me ignore the ordered pairs I comma j, so that 1 less than or equal to I, strictly less than j, less than or equal to n, right? Then if let sigma be an Sn, right? So for each I and j, you look at what happens to sigma I comma sigma j and count the number of inversions. Okay, call it R, say R, right? Then I define sign of the permutation, sign of sigma equal to minus 1 to the power R. Okay, pause, review, proceed. Right? Now we will look at some small n and try to find out the sign of some permutations for such n's. Okay, this is only to give you a feeling what is really happening. Okay, then we will use a very neat trick which will allow us to do something much faster and better. So let us assume n equal to 2. Then S2 has only two elements, only one identity element, identity or the transposition 1, 2, right? Right. Now this is your sigma. And let's look at the ordered pair 1, 2. Let us apply sigma to this. What do I get? I get sigma 1, sigma 2. Okay, I am applying. Okay, but this is 2 comma 1. Therefore 2 is greater than 1. Therefore sigma introduces an inversion or induces an inversion. Therefore sign of sigma should be equal to minus 1 to the power 1, which is minus 1. Minus 1. Okay. Now let's look at n equal to 2. There are many elements. Let us just do some simpler elements only. Yes, sorry, n equal to 3. In S3, let us look at. Suppose I take 1, 2, 3. Sigma is 1, 2, 3. This is a cycle. 3 cycle, right? Okay. Now let us do. What are the two element sets? This is 3 choose 2. That will be 3. That is 1 comma 2, 1 comma 3 and 2 comma 3. Under sigma, where does 1 comma 2 go? 1 goes to 2 and 2 goes to 3, no problem. And here this is 1 goes to 2 and whereas 3 goes to 1, and here this goes to 2 goes to 3 and 3 goes to 1. Therefore there are two inversions, right? Therefore it's minus 1 to the power 2, which is 1. Therefore sign of sigma is 2, right? Just for fun, let's do n equal to 4. Yes, 4. Let us take sigma equal to, let us say 1, 2, 3, 4. 4, 1. This has to be, let us say 2. Then what is left out? 3. Yeah. Let us take this. Okay. Now I am looking at 4C2. That will be lot. Okay. So 4C2 is going to be 4 into 3 by 2, that will be 6. Okay, let us do that. Okay, what are the elements? 1 comma 2, 1 comma 3, 1 comma 4, 2 comma 3, 2 comma 4 and 3 comma 4. These are the two element ordered pairs with that criteria, right? Now let's see what happens to 1 comma 2. 1 goes to 4 and 2 goes to 1, and this is 4 and 3 goes to 2, and this again 4, this goes to 3, and 2 goes to 1 and 3 goes to 2, and 2 goes to 1, 4 goes to 3, and 3 goes to 2 and 4 goes to 3 goes to 2 and 4 goes to 3, right? Therefore what are the inversions? This is an inversion, this is an inversion, this is an inversion, right? Therefore the sign of sigma is minus 1 to the power 3, which is minus 1. Okay, so as an exercise, okay, take sigma equal to transposition 1, 2, 3, 4, right, and find sign of sigma. Okay, and till you do not come. Okay. Okay, so please pause the video and do it, then only you proceed. So you will see all these small things matter a lot. You will soon acquire great mastery over the subject. Okay, I hope you do it. Let's go ahead. So now that we understood, okay, let us do a similar thing for each I and j, I less than j. Let me look at the polynomial xi minus xj. Okay, xi 1 less than equal to I less than equal to n. These are indeterminates. Okay, let me look at the polynomial. Now suppose sigma is a permutation and sigma I is less than sigma j, then the polynomial is I becomes sigma I x minus sigma j. But sigma I is less than sigma j, therefore I can find it somewhere here. You understand that? That's what we did. For example, if it is something like x1 minus x2, my sigma 1 may be x4 minus x7, or it may be x7 minus x5, whatever it is. You understand that? So what I get is this factor will again be one of the elements earlier. Okay, that is, call it this sigma x sigma I minus x sigma j either appears in xi minus xj, where 1 less than equal to I less than j less than equal to n, or the other one appears x sigma j minus x sigma I appears in this, right? That is, instead if you want, write it minus of x sigma I minus x sigma j appears there, because in this case, for example, x1 minus x2 will appear. X1 minus x2, if it is x4 minus x7, that will appear some here. But if it is x7 minus x5, it will appear as only minus of this will appear, that is minus of x7 minus x7 x5, that is x5 minus x7 will appear. Do you understand this? Yeah. So pause, review, proceed. See, now we are ready for the trick. Okay, I already prepared all the ground very slowly. Okay, now you will see how easy it is. Okay, what I do, what is that I want? I am interested in finding the number of inversions which sigma induces among the ordered pairs I comma j, all possible ordered pairs, right? What we found out is, if xi minus xj, either it appears as xi minus some other thing, x sigma I minus sigma x sigma j, or the negative of that appears in that list, right? So if I want to find the number of inversions, remember, what do I want? I want it to raise to the power r finally. If r is the number of inversion, I want to raise to the power r. Okay. Therefore, what is the easiest way to do that? Yeah. Let us go back. I will again illustrate with an example and then define. Let us look at this. In this case, what happened here? So, x4 minus x1. So, all those things which appear, I can write it as x1 minus x2, it appears. X1 minus x3, it appears. And x2 minus x3, it appears. But this appears as minus of x1 minus x4. This appears. This appears as minus of x2 minus x4. This appears as minus of x3 minus x4. You understand that? Yeah. Therefore, the word, it is exactly the same thing, x1 minus x2 to x1 minus x4, and x2 minus x3 to x2 minus x4, and x3 minus x4. This polynomial changed into this polynomial, but for minus 1 to the power 3. Okay. So consider the polynomial in n variables. My f by definition is product of xi minus xj. 1 must be less than or equal to I, but I is less than j, less than or equal to n. Right? So this has n choose two terms. Terms are in this polynomial, right? Now if you give me a sigma in Sn, I define a new polynomial sigma f. This by definition is product. Again 1 less than or equal to I, less than j, less than or equal to n, but it is x sigma I and x sigma j. Is this clear? Notice that that's what we did here. This polynomial is this, but it appeared as x4 minus x1, x4 minus x2, x4 minus x3, x1 minus x2, x1 minus x3, and x2 minus x3. Is that clear? So that is this, right? Now each of these terms, each of x sigma I minus x sigma j either appears in f as a factor, or it's a negative appears. So is that clear? Right? Therefore, what we found is, if therefore my sigma f is minus 1 to the power r f, where r is the number of terms x sigma I minus x sigma j whose negatives appears. In f as a factor. If you get confused, go back to what I asked you to do for n equal to 4. Take the cycle, work out f and work out sigma f. You must already done. Now you see that, okay? This is one of the things we have to learn. When things are very abstract, okay, look at some simple case, but it's not too simple. It's not be trivial case, right? But it's not too complicated, so that you can work out and see what is happening. That builds intuition. This is a trick which you have to learn. Because of time constraints, even though teachers might have learned that way, in the classroom they may not do it. Not that they don't know. Because of time constraint, they have to finish the portion within time, so they have to do it. Okay, don't blame them. They expect, rather they should tell you to do it on your own. Okay, right? Now let's go back. Right? Therefore, this minus 1 to the power r, how do I define it? Is look at f as a polynomial and look at the polynomial sigma f. Right? That is, my sigma f is minus 1 to the power r f. This is called, we denote it as sine of sigma f. Okay, sine of sigma is defined by this number, by this formula. What is that? You apply sigma to f, then I know it has to be either plus or minus of times f, then that sign is you call plus or minus, right? Okay, so pause, you proceed. So what are the things we should notice? We should notice that, therefore, given from Sn, I have a map to only plus or minus 1. Okay, this is called sine. Okay, sine map. So given gamma, I get sine of sigma. Okay, it's a plus or minus 1. Is that clear? Very good. Now, what is the sign of identity? Suppose sigma is identity. Sign of sigma is 1. Is this clear? Because xi minus xj, when I apply sigma to that, it is going to be xi minus xj only. So there is no difference. Right? That's the first example. Next is, suppose sigma is a, let us say, transposition. Right? Then what happens? The original f is x1 minus x2 and x1 minus x3 and x1 minus xn, and then I start with x2 minus x3, x2 minus xn, and go on, then xn, finally xn minus 1 xn. Right? This is the formula. So what will be sigma f? Sigma f, you can see 1 does not appear anywhere in these terms. Only it appears here, right? And here also what will happen? Let me record. This is, I will write only the first term. It will become sigma 2, sigma operating on that will be x sigma 1 minus x sigma 2, which is x2 minus x1. The next one will be x2 minus x3, no problem. And the last one will be x2 minus xn, no problem. You understand? And the rest of the things remain the same, right? And this is minus of x1 minus x2. Therefore, sigma f is minus of f. Therefore, sign of a transposition is minus 1. Pause, review, proceed. So, you have understood that? Yeah? So, we got the thing. Now, we also notice that we also found the sign as a function from Sn to plus or minus 1 is on 2. Why? Sign of 1 identity is 1, whereas sign of unit a transposition is n is greater than equal to 2. Therefore, the transposition 1 2 will always be there in Sn. Do you understand? Therefore, sign of that transposition is minus 1. Therefore, it is an onto function. Correct? Okay. Right. Now, before we go further, just to get a good idea, I will do one step more. So, I asked you to do a cycle, right? Well, let us do it. Yeah? Let us do the cycle. What happens to that? I have to go to screen share. See, this is what I keep forgetting. Yeah. Right. Now, the third example, let us take sigma to be, I will do a simplest case so that it will be easier. My n is 3. Okay, if you want n is greater than equal to 3 is also okay, because it's going to affect. Now what is my f? F1 is going to be x1 minus x2. Maybe I will write a 4, and x1 minus x3, x1 minus x4, and x2 minus x3, x3 minus x4, and x2 minus x4 and x3 minus x4. This is my f, right? So what will be sigma f? Sigma f is, see, 1 goes to this, very easy, right? This is x2 minus x3, and this is x2 minus x4, and this is x2 minus x1, right? This one. And this one, x2 minus x3, what does it happen? That is x3 minus x4 and x3 minus x1, right? The last one, what happens? x3 goes to x4 and x4 goes to x1, right? Now let us tick off. So x2 minus, see, everything which appears the same way, I will make cross it with a green sign. x2 minus x3 is okay, x2 minus x4 is okay, x3 minus x4 is okay, right? Oh, I should have said green, right? Sorry. The green sign. So x2 minus x3 is okay, x2 minus x4 is okay, x3 minus x4 is okay, right? Then what happens? x2 minus x1, it introduces, it's an inversion. x3 minus x1 is an inversion. x4 minus 1 is an inversion. Therefore, this is going to be minus 1 to the power 3 into f. That is minus of f. Therefore, sign of sigma is minus 1. But I want you to notice that it is nothing 4 minus 1. Okay? We will understand why it happens. Okay, just for fun, let us assume n is 1 to n sigma and Sn n arbitrary. Then what do you think f sigma? See, sigma f will be? See, you can see where. So let me write as I did earlier. It is x1 minus x2, x1 minus x3, and x1 minus xn. Next will be x2 minus x3, x2 minus xn, and the last one will be xn minus 1 minus xn. You understand? Now, when I apply sigma, sorry, this is f. When I apply sigma, what happens? I'll just note only this way. This will be x2 minus x3, this will be x2 minus x4, etc. But this will be x2 minus x1. This will turn out to be x2 minus x1. Therefore, this is a problematic one. Right? And here also x2 minus x3 will become x3 minus x4, no problem. Whereas when I come to here, x2 will become x3, but my xn will become x1. Therefore, this is a problem. Right? And similarly, xn minus 1 will become xn, but xn will become x1. Therefore, this is a problem. So, only the last things. Therefore, this is going to be minus 1 to the power n minus 1 into f. Sigma f is. Okay. Pause. Review. Proceed. Isn't it fun? A typically textbook, they will simply take polynomial f and look at sigma f, and then they will say you can see, okay, sigma f and f differ by a sign, that is called the sign. Okay, within 15 seconds, or let us say at most a minute, the sign of a permutation is defined. But you see that we took a lot of time. We understood what we want, we looked at it. Because originally the sign of permutation was done, they were looking at what I started with. Look at the ordered pair ij. Under sigma it goes to the ordered pair sigma I, sigma j, but the relation between sigma I and sigma j may get inverted. Okay, so count the number of inversions and raise minus 1 to that power number of inversions. This is what they did. Okay, right. Have you some idea? Now we are ready for the thing. So what have you done? We defined what is meant by sign of a permutation, and we also looked at examples of a transposition of a small cycle and a big cycle. Okay, very good. Right. The next thing I want to do is very interesting thing. And therefore notice that given any permutation, sign of sigma is well defined number. Either it is plus 1 or a minus 1. There is no change. If it is plus 1, I call the permutation to be even permutation. Right? If sign of sigma is minus 1, I call it as an odd permutation. Okay, I will give the definition, but it can also wait, but let me do it. So, sigma in Sn is even if sign of sigma is 1, is odd if sign of sigma is minus 1. Okay, right. The next thing I want to do is, suppose there are two things sigma and tau in Sn, and f is the polynomial I defined. I want to know what is, see now tau sigma is in Sn. Therefore, I can talk about sign of tau sigma. Okay, I want to know whether it's related somehow to sign of tau and sign of sigma. Is it related to sign of tau and sign of sigma, right? So let us do that. Now, what is tau sigma of f? This by definition is tau of sigma of f. What is sigma of f? That is sign of sigma into f. When tau operates is a number, therefore that number comes out. Sign of sigma into tau of f. What is tau of f? It is sin sigma into sin tau of f. Right? Therefore, we conclude sin of tau sigma is sin of tau into sin of sigma. Understand this? PRP. See now what I have done? Can you see? Now the theorem is easy, right? It's very easy. Right? Sin of sigma tau is sin sigma into sin tau. Very good. And And remember, sine of sigma tau is sine sigma and sigma tau. The right hand side is product of two numbers, that's commutative. Therefore, sine of sigma tau is same as sine of tau sigma. That's all fine. Good. But how to use this? Can somebody tell me? That's where the interesting thing. Now we have seen that any permutation can be written as a product of transpositions, right? And also we have seen any permutation can be written as a in a unique way, but for the order of the cycles in a unique way, the product of cycles, right? Therefore, if I want to compute the sine of sigma, what all I have to do is I have to find out what is the product of, sorry, what is the sine of a cycle or the sine of transposition. Do you understand this? Yeah, right. So let us go. So now suppose sigma is in Sn, okay, then yes, sigma I can write as sigma 1 to sigma k, right, as transpositions. Sigma j I are all transpositions, right? Now notice that this is not unique. Therefore, sine of sigma will be sine of sigma 1 times sine of sigma k, but we know sine of this is minus 1 and product minus 1. Therefore, it is going to be minus 1 to the power k, right? So, I can easily compute the moment I break sigma into product of transposition. But then the very interesting thing is, suppose my sigma is also tau 1 to tau L, again tau j's are transpositions. Let me see whether I am sharing the screen. Yes, right. Therefore, sine of sigma for this guy will be minus 1 to the power L, right? But sine of sigma is a unique number, either it's plus 1 or minus 1, there is no change. Therefore, what is the conclusion? Therefore, I conclude minus 1 to the power k is minus 1 to the power L. This, what does this mean? This means k and L have the same parity. What does it mean? That is, this means either k and L are both even or both odd. That's it. So, what is the conclusion now? So, now suppose my sigma in Sn is even, right? Then if I want to write it as a product of transpositions, then how many transpositions will be involved on the right side? It has to be even number, right? The number may differ, but it has to be even number of transposition. You understand? Sigma is even permutation. Then I can write it as sigma 1 to sigma k. This k may not be unique, but has to be always even. And what can you conclude about odd? I'm not going to say that. You know that. Yeah? Very good. I don't want to say it. Okay. So remember, this is what in the end of the last session I said it. What did I say? If sigma is any permutation, the way of writing as a product of transpositions is not unique, but the number of transposition involved in each expressions are always either even or always odd. Okay, we proved it. Is that all right? Great. Now let's go to the next one. Now suppose sigma in Sn is a cycle, right? Let us say A1 to AK, right? But remember, this we have written as a product of, this is my sigma, I got written as a product of transposition A1 AK, A1 AK minus 1 and A1 A2. So how many transpositions are involved? my k minus 1 transpositions. Therefore, sine of sigma is minus 1 to the power length of sigma minus 1. Length of sigma is k. Okay. Are you following? Now you see that this is what we found out earlier. For example, sigma is a transposition. Length of sigma is 2. Therefore, it's minus 1 to the power 2 minus 1, which is minus 1. Correct. And when we also saw length sigma, we took a cycle, right? 1, 2, 3, 4 or something. Then we found out it is minus 1 to the power 4 minus 1 minus 1. Okay. So these things we already know. Have physically checked. Okay, already checked manually. Right? Oh my gosh. See, this is what happens. Now, let us see. Suppose this is where I have to start sharing. Suppose sigma Sn is a cycle, A1 to AK, then I call length of K is K. Okay, we have written as a, in fact, we wrote in two different ways, but let's look at one. Okay, sigma is A1 AK, A1 AK minus and A1 minus A2. Okay, it's a product of transposition. How many transpositions? K minus 1. Therefore, sine of sigma is going to be minus 1 to the power length of sigma minus 1, which is minus 1 to the power K minus 1. Right? We had already checked it for transposition. Transposition, we know it is minus 1, that is minus 1 to the power 2 minus 1. And also for this cycle, 4 cycle, we had checked it earlier. These are all the things. Okay, very good. Now the question I want again is, what does it do? What is the obvious application for this? We already said it. But you see the simplicity now. Now suppose sigma is a permutation. Okay, we know how to write it as a product of cycles. It's very easy. How did I do? I start with 1. Where does sigma 1 goes? And sigma 1, where does it go? And finally I will come back to 1. Then in the complement, look at the smallest integer. Then start from that. Okay, let us say it is, let us say 7. Then sigma of 7. Then like that. You keep doing. Okay, so we wrote as a product. So writing a transposition, sorry, a permutation as a product of cycles is easy theoretically, right? Suppose there are trillion terms. Okay, do I want to do that anyway? Okay, so in principle it's easy, right? And therefore now once I write as a product of cycles, each of the length is known. Therefore I know what is the sign of the permutation itself. Do you get it? Okay, I'll do it. With that we will stop. Now suppose sigma is a permutation Sn and sigma is, let us say, tau 1, tau k, where each tau I is a cycle, and length of tau I, let me say Li, right? Therefore I know sine of sigma is sine of tau 1 product sine of tau k. But I know this is a cycle, therefore I know its sign. It is L1 minus 1, and this is Lk minus 1, right? Therefore the sine of sigma is minus 1 to the power L1 plus L2 plus Lk minus k, right? But what is L1 plus L2 plus Lk? Right? When I write this as a product of cycles, even the cycles of length 1 are included. You understand that? For example, suppose I have something like 1, 2, 3, 4 and 3, 2, 1, 4. Then I will write as the 1, 2, 3 or no, 1, 3, 2. Oh, 3. No, I saw, sorry. 2, 3, 1, 2, 3, 1. It will be easier for me. Okay. So I will write it as 1, 2, 3 and then this one. Therefore, what will be the sign of this permutation? This will be minus 1 to the power length, minus length is 3, therefore 2, and this is 1, therefore it is positive. You understand that? Or if you want to say 5, then I will write it as 5 only. Okay. So what I want, if I otherwise, if you superpose, if you leave it, then I'll have a problem, right? So I am considering as 1, 1, 1. Therefore, summation length 1, length k equal to n. Okay. So please understand. Therefore, sine of sigma is n, sorry, minus 1 to the power n minus k, where k is the number of cycles. I hope I'm correct. Let me just make sure I have not done any mistake. Yeah, right. If there are one, they will also get cancelled. Right? If cycles of length 1 come, that one will get cancelled. Therefore, I'm correct. Okay, right. Okay, that's it. So this formula is usually done in books, but it's a pretty nice formula, right? So suppose I take now some horrendous looking permutation, okay, and can I find out its sign? Yes, I only have to write it as a thing. So if you want, let me just quickly do something. I do not know whether I have already done it. Just give me a minute. Yesterday I think I did. Yeah. Okay, I have a permutation. I have done it just for fun. Let me just do it. Okay, as an example, let us assume 1, 2, 3, 4, 5, 6, 7, and this is 3, 7, 2, 5, 4, 1, 6. Therefore, let us start with the cycle. 1 goes to 3, 3 goes to 2, 2 goes to 7, 7 goes to 6, 6 goes to 1, right? And 4 and 5. Is that clear? Right? Therefore, what is that? The sign of sigma, right? Minus 1 to the power length of this. Okay. This is what is the length? This is n. This is 7 minus 2 cycle, therefore it's negative. Minus 1. You understand that? This n is n minus how many cycles are there? 2 cycles. So you see how life is easy? Yeah? Right. I hope you did that. There is one more last thing. I thought I had covered everything, but there is now if I give me a permutation, either it is even or odd. Okay, it's mutually exclusive cases. Right? Therefore, my Sn is partitioned to two subsets. One subset consisting of all even permutation, another subset consisting of all odd permutations. So I would like to know, do I know how to find the number of even permutation and the number of odd permutations? Is the question clear? We will answer that. Okay, with that I think I would have covered everything. I guess we will leave it. So let us look at that. Let us look at Sn, right? Okay. Then the standard notation is An. An is all sigma in Sn, so that sigma is even. That is an even permutation, right? Therefore, from An, and let us say odd n. Odd n is all odd permutations. Okay. Let me at present look at only Sn, right? And now suppose sigma is an An and tau is this transposition 1, 2. Remember, my n is greater than or equal to 2. Therefore, this transposition will always be there. right? Now what will be sine of sigma tau? That will be sine of sigma into sine of tau. That is, this is 1, this is minus 1, therefore it's minus 1, right? You understand? Therefore the map, call this map phi from an to Sn, sigma going to, I will fix this tau, okay? This notation for tau is fixed now, sigma tau. Then what I know is this actually lands in odd n. Odd n is odd permutations. Yes, right? Okay. Now I want to claim this map phi is 1 1. Okay. Why? Suppose phi of sigma 1 is phi of sigma 2. I have to know whether sigma 1 is sigma 2. But what is phi of sigma 1? Sigma 1 tau, and this is sigma 2 tau. Right? Now remember, tau is a transposition. Therefore, tau times tau is tau squared is 1. Right? Because if ij is that transposition tau, then tau squared will be, you understand this? I goes to j, tau is what? I goes to j, j goes to I. Therefore, apply once more, I goes to j and j goes to, let me write it, I goes to j under tau, under another tau j goes to I, and j goes to I, another I, and this I under tau goes to j. Therefore, tau squared is identity. Therefore, if I say sigma 1 tau equal to sigma 2 tau, then multiply, operate tau on both sides. But associativity by this is tau tau equal to sigma 2 tau tau. But what is tau tau? It's identity. Therefore, I get sigma 1 equal to sigma 2. Right? Therefore, phi is 1 1. I claim phi is onto. What does that mean? Okay, suppose you give me an alpha in odd n. Right? Then alpha times tau, what is the sign? That will be sine of alpha and sine of tau. Both are minus 1 into minus 1, therefore it's 1. Therefore alpha tau is, therefore given alpha in odd n, take odd suffix and take sigma equal to alpha tau. Then sigma is in even permutation. And what is phi of sigma? Phi of sigma is alpha tau tau, that is alpha tau tau, that is alpha. So it's on to. Is that clear? So pause, review, proceed. So what have we shown? We have shown there are a one-to-one a bijection between even permutations and odd permutations. That is, there are as many odd permutations as there are even permutations. But remember, my Sn is a disjoint union of these two. But what is the number of elements in Sn? It's all permutations of the n symbols, that is n factorial. Therefore, how many odd permutations are there? How many even permutations are there? Half of that. Therefore, number of even permutations is half of n factorial. Number of odd permutations is half of n factorial. That is the result. Okay, I will write down the result. With that, we will stop. Sn is an union odd n. This is a disjoint union. Therefore, number of elements in Sn equal to number of elements in an plus number of elements in odd n. But this is twice the number of elements in an because there is a bijection. Therefore, number of even permutations is half of n factorial. Therefore, odd permutations also half of n factorial. Okay, I think I have done everything whatever I wanted to say about permutation group. I hope you all enjoyed. Okay, right. Before ending, there is an announcement. Due to some personal work, I will be away. Okay, for the next after making this video public, next 2 to 3 weeks, there may not be any video on group theory for a while. Okay, in all probability, once I resume, I will start with the dihedral group. I'll spend just one session completely on dihedral group because that one is most often not done. But in my humble opinion, in the first course in group theory, the basic most important examples of groups for me are ring of the additive group of integers and integers modulo n, and then symmetry group and dihedral group. And apart from that, there are also matrix group. We had already seen group of n cross n invertible matrices. There are few more groups. We will introduce it when we learn subgroups. Okay, these are the very important examples. For some strange reason, even algebraists do not do dihedral group. Perhaps if they do what a very long thing when they would introduce generators and relations. Don't worry about such a jargon. Okay, we will do all those things later. Okay, so perhaps I will start with the dihedral group when I resume the thing. Till then, enjoy and don't forget, review your elementary number theory. I think I had uploaded about 6-7 videos there. Okay, please go through that. I think I have done GCD LCM and also congruences. Okay, please go through all of the things so you will be raring to go. Okay, all the best. We will meet again.